Hey there, Captain Squad. In today's class, we're going to talk about kinetic molecular collision theory. Alright, so there are 6 factors that influence the rate of a reaction. Can you name them? I hope so, because they're right there. The first one is temperature, concentration, volume or pressure, surface area, catalyst inhibitor, and nature of reactants. So these 6 factors all help to increase the rate of a reaction from reactants turning into products. But out of these 6, only 4 of these, okay, uses what we call the kinetic molecular collision theory, or KMCT for short, to describe how these reactants have to behave in order to increase the rate. So they do so by something called effective collisions. Okay, and we'll get to that in a minute. But out of the 6, it's the first 4 here that actually uses the kinetic molecular collision theory. Okay, and if you remember from our lesson dealing with those 6 basic factors, okay, temperature, concentration, pressure, volume, and surface area, they all greatly tie into where their molecules are and how they collide with reactant molecules in a reaction. Okay, so these 6 here are influenced by the kinetic molecular collision theory. So let's take a look at what this kinetic molecular collision theory is. Okay, so when you have molecules, okay, so let's say you have 2 molecules here. Okay, if you give them a certain amount of kinetic energy is the energy of motion, or energy of molecular motion. So whenever we add heat to molecules, right, we give them more chance to vibrate, okay, if we add more heat. So let's show it like this. Okay, the more heat they have, as an example, okay, the more kinetic energy they have. The more kinetic energy they have, the more likely that these guys can move around and collide. So if they collide, it gives us the opportunity to make or break bonds. Okay, so the interaction between these 2 molecules now are greatly affected by their collisions. Okay, but it's not any type of collision. It has to be an effective collision. So let's look at what effective collisions mean. So effective collisions are it happens when atoms or molecules collide at proper angles and velocity, which is basically speed with a direction. So when atoms or molecules collide at proper angles and velocity, bonds between these atoms or molecules can either form or break to produce products. Okay, that's the ultimate goal. When atoms and molecules collide at proper angles and velocity, the bonds between these two atoms and molecules, okay, they can either form, or in some cases they might have to break in order to produce your products. Okay, so that's what effective collisions are. So let's take a look at these effective collisions in terms of an analogy. Okay, so analogy is just something where it's like an example, but since we're talking about chemistry, it's usually a non-chemistry example. Okay, so that means that it's a comparison in a different context, in a different situation or scenario. All right, so let's look at a car crash. So, for example, I was in a car crash about 20 years ago, had a head-on collision between a car that was basically, we were both at an intersection near the U of M. Okay, so this was their car. Okay, this is my car here. I was going straight. This guy was making a turn. Okay, my car. I was at the time driving a Honda Civic, and I believe he was driving some kind of Ford. Okay, we're both about mid-sized cars. Okay, but he claims that he had right of way. I claimed that I had the right of way, and in this hit, in this collision, okay, his car had no damage. Okay, so his car just seemed fine. My car had a whole bunch of damage at the bumper. Okay, pieces of my car was falling off. But I was kind of sitting there thinking, oh man, I hit this car, and everything was in slow motion, right? So we're both heading to each other, and then we hit. A lot of damage on my car, little damage on his. So it all depended on how we both collided. And during this moment, I was thinking to myself, okay, when it hit, I can clearly see afterwards that the guy that I hit, he basically stepped out of his car, so he was fine, and he kind of approached me, and I was just grabbing onto my steering wheel, and all I could think of was, there's no airbag. Okay, so my car was a much older car, and apparently airbags weren't installed in it. Okay, and I had no clue, and I was thinking to myself, wow, like I could be thinking, oh man, I could have killed someone, or I could be seriously hurt. Okay, at this point, I haven't even gone out to see the damage on my car, but I was just thinking, wow, there's no airbag. Okay, that's messed up. Like, where's my airbag? But fortunately, I was fine. The other person was fine. But depending on the angle of the collision, depending on how fast both vehicles were moving, okay, I ended up with more of a significant damage, and he ended up with nothing. Okay, so effective collisions make all the difference. So if we take a look at an actual example with molecules now, okay, we'll kind of translate how these effective collisions can either make or break bonds. Okay, so remember, in my case, the collision was pretty effective, okay, at totaling my car, but nothing happened to the other person's car. It was ineffective on him between our two collisions. So if we look at an actual example, we'll use a bit of color here, mostly just to identify the differences between molecules here. So let's say I have hydrogen gas. Okay, that's what we start off with, and we're going to add it to iodine gas. Okay? So both of these are going to react. Okay. Now, according to reaction, it will form two molecules of HI. Okay. That makes sense because we have two atoms of hydrogen, two atoms of iodine. However, in chemistry, when two reactants combine together, okay, they don't immediately make the final product. Okay. There has to be a significant collision between the two molecules first. So this one here, so let's say, oh, lost. Okay, there we go. So let's say there's a collision that happens between these two molecules. Okay, this is scenario one. Let's say the collision was ineffective. Okay, they both collided with each other, but because the collision was at improper angles and not at the correct speed, nothing happens. Okay, they basically bounce off each other and they still remain separated. Okay, so they go about their own way. So no bonds form or break. Okay, essentially no reaction. Now, in scenario 2, we have the same situation. Okay, but let's say that in this situation here, the iodine molecules and hydrogen molecules came at each other from different angles and different speeds. Okay, so let's say it came this way and this way, and they collided. Right? If this collision is effective, then what might happen is that you get some kind of a bond forming. Okay. So let's say it was something like this. Okay, so in this scenario, oops, bonds form. Okay, and an intermediate molecule is produced. Now, we'll talk more about these intermediate molecules in the next couple of lessons or so, but right now you have the hydrogens and the iodines forming a bond between them. Okay, so this is one whole molecule, okay, one whole particle, okay, that we call an intermediate. Now, like I said earlier, most things in chemistry, they don't go from start to finish right away. Okay, there is an in-between step, and this is the in-between step here. So once you have molecules colliding at proper angles and speed to form an effective collision, okay, typically there's an intermediate molecule that's formed. These intermediate molecules might collide with other intermediate molecules in such a way where their bonds eventually break. Okay, I'm not going to show that step here, but I'll just show you what the final product might look like. So after more collisions, okay, you'll eventually have your iodine and your hydrogens, okay, bonding together. So that makes one molecule there. And you'll have another set of H and I, okay, having bonds forming between them, making two separate molecules of HI. So you get your final products here. Okay. But of course, all this doesn't happen unless you have effective collisions. So at every step of the way, okay, going from your initial reactants, they collide, there's an effective collision, okay, to form your intermediate molecules. These intermediate molecules will also collide with other intermediate molecules effectively to form your final products. Okay, so when they are in scenario 1, when they do not form effective collisions, so ineffective, oh, that's not how you spell ineffective, sorry. So ineffective, nothing happens, no bonds form or break, and they basically remain the same as they were before. Okay, but in scenario 2, when there are effective collisions, everything happens quicker and faster to form your final products, and we basically say that any factor, okay, any factor that increases the number of effective collisions will therefore increase the rate of reaction. Okay, so temperature, concentration, surface area, pressure and volume changes, those four factors will all influence the number of effective collisions. Okay, catalyst inhibitors, nature reactants, they do not do this. Okay, they increase the rate of reaction in their own special way, but not through effective collisions. Okay, so to summarize everything, according to the kinetic molecular collision theory, when we increase the number of collisions between reactant molecules, we will increase the number of effective collisions, so that bonds between molecules can form or break to create products, thus increasing the rate of reaction. So hopefully this gives you a little bit of insight in terms of how reactants can form products more quickly. Okay, we will take this information, of course, and we'll apply it to future lessons, okay, to continue on our conversation of how certain types of reactions will react faster than others. Okay, well, that's all the time I have for today. Take care. Thank you for listening.